Okay, here we go with the supplemental review problems, picking up where we stopped in class. With the next problem on the list, number 5, we're doing a principal value of an improper integral. So I want to think of this like it's a complex function, and so thinking of z to the 4th minus 1, these are the 4 roots of unity. And so we've got z minus 1, z plus 1, and also plus or minus I. So there are the 4 roots of unity. And that tells me where my singularities lie. We're integrating from minus infinity to infinity on the real axis. So remember, this is where we need to think about singularities on the axis and singularities in the upper half plane. The only singularity in the upper half plane is at I. Okay, and then we've got these here, and then one that I don't care about in the lower half plane. Okay, so the residue at I is, just plug I in here, and I think that a nice shortcut here, instead of plugging I into 3 things and hoping I multiply them correctly, I'll just plug it into the derivative of z to the 4th minus 1, which is 4z cubed. So I'm just going to plug I in there because this is obviously a simple pole. So that gives me the formula for the residue, and I get negative I over 4. And then on the real line, we have singularities at plus or minus 1. And those are simple poles. So again, same formula. I can just use the derivative of the denominator, and plugging that in, I get, I guess, plus or minus 1/4. Okay, so the answer to the problem then is we multiply the residues in the upper half plane by 2 pi I, and we multiply the residues that happen to fall on the real axis by pi over I. And again, this only applies to simple poles, and so those actually cancel out. So we'd get the same answer here if we actually forgot about those, of pi over 2. Okay, so remember, this integral technically diverges, but we have this Cauchy principal value to assign some kind of value to it using residues as the what we call big R goes out to infinity there. Number 6. It's another residue calculus problem. Okay, and this time what I don't want to do is look at cosine of z, because I can't control what happens to that. It has an essential singularity out at infinity. Instead, the function I want to look at is e to the iz, and then when I factor, I have z plus 2i, z minus 2i, and z plus 3i, z minus 3i. So we're going to look at this function, and the residues that I'm interested in are in the upper half plane. So I'm interested in the residue at 2i and the residue at 3i. These are simple poles, so again, computing the residue is not that hard. I plug into my formula here. Let's see, I plug in 2i, so 2i plus 2i is 4i, and then we're covering up the z minus 2i factor that's here, and then z plus 3i, so I'd have 2i plus 3i is 5i, 2i minus 3i is negative I. So again, this time I decided to do the cover-up method instead of the derivative method. Whatever makes sense, either way is fine. And I end up with, what's this, 20i. Very similar for the residue at 3i. Plug in there. I get 5i, 3i minus 2i is I, and then 6i, and then we've covered up the last factor. So that gives me e to the negative 3 over negative 30i. So those are my residues. The answer to the question, remember I'm integrating a real integral here, the cosine of x. So the integral that I seek is actually the real part of an integral whose value is 2 pi I times the residues. So plug in the two residues there, multiply by 2 by I, take the real part, but everything I guess is real here. So I'd have cancel the 2's, and then I have a 15 e cubed. So there's my solution to this residue integral. Number 7 is looking again at a linear fractional transformation. If I want the inverse, here is my function, and I just want to solve for z as a function of w. So let's multiply this over to the other side, and let's get the z terms together and get the w terms over here, so I can factor out z on this side, so I have w minus I over iw minus 1. Okay, and normally I guess we would, instead of using w, I don't know, switch letters here and call it z, so I get this function. And incidentally, I don't know if you had a reason to suspect this or not, but notice that L happens to equal L inverse in this case. Okay. What's the image of the real axis? So here's the real axis, and I think the easiest way to do that is just to plug in some points that are on there, like 0, and 0 maps to just plugging in 0 into my original function, and I get I. 1 is on the real axis, so 1 minus I over I minus 1, that's just negative 1. And we can try another one here. We can try negative 1 if you like. Negative 1 minus I over negative I minus 1, that just equals 1. Or another point you could check that is on this line, at least in the Riemann sphere, infinity lies on this line, because a line is just a circle that goes through infinity. And we can see that infinity maps to, well, when I take z approaching infinity in modulus, I'm just looking at these leading coefficients right here. And so I just get 1 over I, which is minus I. So I've done more than I needed to do there. I've come up with 4 points. Remember, I only need 3. So let's see what these images are. So 0 maps to I, 1 maps to minus 1, negative 1 maps to 1, and infinity maps to minus I. And you will quickly notice that these points have to lie on a line or a circle, and in this case it's the unit circle. Number 8 looks like a conformal mapping sort of question. I apologize for we've got degrees Celsius, and then we've got like degrees of angle measure in the same problem, and so that seems like kind of a bad idea. I probably should just call this pi over 3. If we multiply by z cubed, that's going to unfold this thing and spread out this angle to now be an angle of pi. So remember, conformal mapping z cubed is conformal everywhere except at the origin, and that's because it triples the angle right there. So this is going to spread out my picture this way. Okay, and that picture looks familiar, and maybe you already know the solution there, but we could keep going here. The reason we knew the solution to this kind of question was because of the complex log function. And the log function is going to take me from things that have an argument of 0 up through things that have an argument of pi. So this would be pi I. And those angular arrays of constant argument are now mapped to horizontal lines between 0 and pi I. So this is an infinite strip. And again, maybe the solution is kind of obvious here, but we could keep going if you like. Let me rescale this by multiplying by 1 over pi. So now we've shrunken our strip down so that it just goes, it has width 1 now, so this would be the point I. So now the width is 1, and let me take one more step here. If we multiply by e to the negative pi over 2, also known as multiplying by minus I, that's just a rotation clockwise. So now my picture is a very standard looking, this is 1, this is still 0, and now I have these vertical lines would be my lines of constant temperature, my isotherms. And I claim that the solution should be pretty obvious over here, that T is going to be the, well, it's just, let me remind myself what my boundary conditions are here. We're 0 here, and then we need to reach 50 degrees over here. So to go from 0 to 50, I just multiply 50 times x, x also known as u, because I'm in the UV plane, also known as the real part of w, if we think of this as the w plane. Okay, so if we pull that back then to the original under this conformal mapping, and if I could get the composition correct here, I have 50 times the real part of w, and what is w in terms of z? It's what I get when I take z cubed, and then I take the log of that, and then I divide by pi, and then I multiply by minus I to rotate it. Gives me that thing. Okay, and so we could do some simplifying here. That gives me t as a function of z. I might be interested in writing t as a function of x and y, more likely. So this is the real part of, if we write out what log means here, I have negative I over pi times the natural log of z cubed, and then plus I times minus I is just a plus 1. So I just have 1 over pi times the argument of z cubed. Okay, so that minus I means that the real part is actually sitting over here now, and because we've now picked up this imaginary part on the log here. So my temperature function, we take the real part here, is just 50 over pi times the argument of z cubed. Okay. Well, and maybe at some point I should have used the log property here. I think would have made this a little simpler. So let me go ahead and do that. This is 50 times the real part of minus I over pi. I can bring that 3 out front, so this is now 3 times the log of z. Okay, I don't know that we ever specifically talked about that for the argument function, but I can get rid of this 3 here and now stick it out front. And the argument of z cubed is actually just 3 times the argument of z. So multiplying by 3 here, I get 150 over pi times the argument of z. And again, we may want this in terms of x and y. So let me write t of xy is 150 over pi times the argument of z, when in the world of x and y would be the inverse tangent of opposite over adjacent, or y over x. Okay, so this might be a good answer here for my temperature as a function of x and y, which is what they've written there. We were also asked about finding the complex potential, and you can see it right here. I've already written t as the real part of something, and so remember t is the real part of the complex potential. So my complex potential f of z is just given by what I have here, negative 50 I over pi log of z cubed, or if you want to bring that cube out front, I guess it's negative 150 log of z. Okay, so there's my complex potential function. We didn't look at the imaginary part of f. Just remember the imaginary part of f would give me the heat flow lines. Usually called that thing psi. So this would be the heat flow lines. And I guess in this case, since I'm writing it down, it would be, what do we have there? Negative 150 over pi natural log of z. Right? Because the flow, if I go up to my original picture here, the flow are just these circular arcs that only depend on the modulus. Okay, and the only harmonic function I know here that is a function of the modulus is the log function. So that makes sense there for my flow lines. Oh, I guess the instructions also said reinterpret this problem in an electrostatic context. So I suppose that means instead of this being a temperature, this is now an electrostatic potential. This is 0 kilovolts or something, and instead of this being a temperature, it's an electrostatic potential. And so my temperature, which is the heat potential, is now the electrostatic potential, and these heat flow lines become the lines of force. And we've got this complex potential for a electrostatic context. Okay. One more question here on the sheet, talking again about these potentials, in this case the context of fluid flow. So let me do more than maybe I need to answer this question. So F here, again, we just did this work on the previous problem, but let me do it again. That minus I just has the role of basically swapping the real and the imaginary part, because it rotates your picture. So minus I times the log of z, we write out the definition of the complex logarithm, and I get this guy. Okay, and so we end up with positive arg z for the real part, and then I guess minus I times the log of z for the imaginary part there, because minus I times I is positive 1. And remember, we called the real part of the complex potential, this was my velocity potential. But for these problems, we were more interested in actually the imaginary part here, which, let's see, I need to make sure I don't lose that minus sign, so let me include that in there. And we'll call this thing, these are our streamlines or our flow lines, are given by the level sets of this streamline function. Okay, so if the level sets are given by the log of the modulus, then level sets of the flow depend only on the modulus. So here's 0, and that means my flow lines are just concentric circles. Okay, things are, well, I don't know which way it's going yet. That's the question. But these are my flow lines. The potential lines, that's the argument function. So these are lines of equal potential going out like that. Okay, and remember the velocity here of this thing is given by the gradient of the velocity potential, and so that's going to be perpendicular to these level sets. And again, I guess I'm already assuming it's counterclockwise here, but we've got these, this is my vector field going like this. Okay, so I can think of v that way, or remember that v as a complex number velocity is given by the conjugate of f prime. Okay, and so I know what f prime is. It would be minus I times the derivative of log is just 1 over z. If I take the conjugate here, be careful, the conjugate isn't just I times 1 over z. It's I, but then I also need to take the conjugate of 1 over z, which is 1 over z bar. Okay, and to simplify that a little bit, let's multiply by z over z. So my velocity looks like I times z over, this is a fraction bar, sorry, not a conjugate bar. Z times z bar is the modulus of z squared. Or written in terms of x and y, it would look like this. Okay, so I'd have negative y plus I times x over x squared plus y squared. Okay, and you can see from that vector field, or if you're not sure, we could even plug in a few points. So which direction is the vector pointing, let's say, at the point at 1, which is, let's say right over here somewhere. If x equals 1 and y equals 0, then we're pointing in the the complex number I direction, also known as the vector j direction. Okay, and if you plug in I, you get the vector is pointing in the negative x direction. Okay, so I think just plugging in a few points here allows me to determine that, yes, this is going counterclockwise, and it's what we might call a vortex that's swirling around z equals 0. Okay, and we'll stop there. Good luck on the final, everybody.